Okay, so I might just give a recap. So let me solve, look at two different problems. In this hands-on session, let's look at two different type of problems. Let me look at one problem, which is, oh, I have disconnected my tablet. So one problem will be, so both the problems we will solve using a multi-layer perceptron, MLP, or what is popularly known as the backpropagation neural network. And in one problem, we will solve a regression example, a very simple y versus x, so that we can plot it and see it. And in the other example, let's try to do this exclusive OR classification and see how it performs. Okay. So, so those are the two problems. So let's look at the Matlabs Toolbox, ANN Toolbox. Okay, it has a very nice interface.
The MATLAB is not visible. I don't know if this is problem from my side or.
Oh, because I am sharing. So what is visible?
It's just blank. Some.
Oh, I understand. I should share the screen rather than sharing an application. Then when I switch, it will switch accordingly.
Yeah, now it's fine.
Yeah. So I was trying to write down the agenda. So first we can try using the MATLAB toolbox, the ANN toolbox, which has a very nice interface. And in this, let's attempt one regression problem and one classification problem. Okay. So what we have in the regression problem is a y versus x data. So it is some y versus x, and I don't remember, it looks some curve. Okay. And we will try to fit a, so because you have a toolbox, you can try, you can try with many layers and so on. So in this example, I will use, so the number of inputs will be 1. And I will put some S neurons in the hidden layer, and number of outputs will be 1. Okay. And of course, you can choose many different options of the activation function. Maybe I can use log sigmoid or logistic sigmoid as my function, activation function. In the classification problem, I will just try using XOR, exclusive OR, and see whether, a neural network with one hidden layer can try to solve it. And after that, as I was trying to suggest, that I can just simply go to some modern neural networks, and two neural networks that I would like to talk to you about is the Convolution Neural Net and the Lstm Neural Net, which is nothing but a recurrent neural network. Okay. Now, there is, Google has a software called Tensorflow, which has become extremely popular, and you will be surprised that most of your students would have already heard about it or used it, because there are a lot of tutorials and online classes and so on and so forth, which is available. And TensorFlow has, you can either call TensorFlow in Python through some APIs, or you can call it in R. Okay. Now, yeah, I may not be able to show you this because I don't have my machine with me, but I'll just basically just briefly discuss with you about TensorFlow. Okay. And the thing is, with these toolboxes, you can start solving significant problems, even though you are doing it without, very quickly. For example, you can just download an image of yourself and you can train it to identify. Okay. So you can, I give it many images, let's say of 2 different people with names, and I say, okay, this image belongs to this class, these images belong to that class. and then you give variants and it will start working. Okay, so that is very often convolution neural net. And this, as I told you, so you can give weather data, financial stock exchange data, or you can just give dynamic systems, and it works. It works extremely well. So this TensorFlow allows. I'm not sure if TensorFlow has an API with MATLAB. It probably does, but I have used it in R, and a lot of my students have used it in Python. So um, so yeah, let's start. So I will go to MATLAB. I have already opened that example. So I think what this example is the regression example. So I'm going to load this data set called simple fit data set. This is available as part of standard data sets in MATLAB. So you will see that in almost all the softwares, there are these standard data sets available. Okay, so at least for teaching purposes, you can very quickly, because the first question is, where is my data set? And so in R, so there are many data sets which are in repositories all over the world, and they can be read off directly in R or Python. And so, you can start doing demonstration with quite significant type of problems in class. Okay, so let me just load it. Okay, now I think what I could do is, so this is my raw data set. Okay, and I told you the first thing I would like to do is scale it. But let's look at the raw data set. So I will do plot train data inputs raw. These are the inputs, the X, and train data outputs raw. Okay, so at least so this is that curve. Of course, you will say it's not a curve. There should be points, and so I will just make points. Those points. Okay, so I can, for example, look at the size, and I know that there are 94 points that I have, which is not a very large data set. So first thing I do is do that scaling, scale the data, and let's see if we have. So we have just said scale the inputs now. So I think it is a 0, 1 scaling, and we will replot it. So we that the original data was from 0 to 10. Okay, and let's see what the scale data will be. You can see the scale data is from 0 to 1. Okay, so this is the scale data. So as I said, the first step is pre-processing. Now here, of course, there is no feature extraction. There was just X. But in any real problem, that is a significant problem to solve before you can start using neural nets. Okay. Now the next step, of course, is after we have seen our input data, that we have this prototypes P vector, which for me is going to be a column, and the T vector, which is the targets. So basically it is X and Y. And I've defined those. Now is the time to go to neural networks. So, the neural network toolbox in MATLAB has undergone a lot of changes. And this MATLAB that I have is 2016 version. So, there's a command called new feed forward, new FF. Now, if you see that these arguments should make a lot of sense to you. So P, of course, is your input. T is the target. S is a vector of the number of neurons in the hidden layer. Okay. TF is the transfer function. For example, if I want to use log sig, the name is log sig in MATLAB. If you want to use 10 sig, okay, there are many such transfer functions that you have. And then I have BLF is let me just pull this a little down. So BLF is the or BTF is what type of training function you want to call. So for example, train LM is training using Levenberg-Marquardt. So, for example, for those of us who've done curve fitting in MATLAB, we know very often it uses Levenberg-Marquardt. And then you have the learning function, which is learn GDM is gradient descent method. And then the performance function, what you want to minimize, and it is mean square error. And just using this, so let's see what is our neural network. So my ANN uses that X value in P, the Y value in T. I'm going to say that the number of nodes in the hidden layer are 3. So just one hidden layer. If I put 3, 4, it'll become 2 hidden layers, right? So very simple. And then I'm giving the transfer function. The first transfer function from of the hidden layer is going to be log sigmoid, and in the output layer will be pure len. Now, of course, I don't need to specify how many neurons in the output layer because they get fixed by T, the output. Okay. And instead of using train LM, I can use train BR, which is Bayesian regression or Bayesian regularization. Okay. So let's generate this empty object now. So you see, I have already created my ANN object and it is shown. Some parts I have specified, others it has put as inputs. And you'll see that it gives you access to a lot of options. So in this case, number of inputs is 1, number of layers is 2. You can see number of outputs is 1. You can put delays, okay? You can, you have a lot of scope to be able to specify what type of neural network you want to make. Then if you don't want a bias somewhere, you can make it 0 over there. You don't want an input, or you want an input to connect directly to the output layer. That is also possible. Okay. And so on. So there's a lot of scope for playing around. Now, you will see that, it has this input weights, layer weights, biases. This is where it is storing its values. So for example, I wonder if I can remember, but let me look at what are the bias values which are there. So my ANN dot, so weights and bias over here are in IW for the initial weights, LW for the layer weights, and so on. And you can see that these are the values. So I think if I do it like this and I do 1, these are the default values that when you created a neural network, it already inserted for you. So, if you did not want default values, so somewhere the default option is that, select my initial weights and biases randomly. If you don't want, you can turn it off and you can specify that these are my initial weights and biases. So that ability to maneuver is there with you. Okay. So you can now, because there were 3 neurons, I think there were 3 neurons. So there are 3 initial weights from P, that X value, to neuron 1, neuron 2, neuron 3. Okay. I can see what are my layer weights. And I can make this as second comma 1. And these are my layer. So it is from the hidden layer to the output layer. There are 3 neurons. They're connecting to one output layer. So there have to be 3 weights. So these are the 6 weights. And you can see their values, which have been randomly put. Okay. Now that we have seen how to define or initialize a neural network, you might be interested in seeing, okay, let me run this neural network for my P and see how well it does. This is an untrained neural network, just randomly assigned. Is it any good? Okay. And you could run this. Oh, it's running the whole thing. I wanted it to run just this. Oops. I should have pressed F9 and I instead ended up pressing. So let me just come to that point again. So this is the definition. Yeah, so just let's run it with just those randomly initialized weights and plot it and see how does it work. So let's compare it with the outputs. So we'll plot it and look at that. See the blue X's are is the output of the untrained neural network. We have not used the backpropagation algorithm yet. Okay. So we say, okay, now I have my targets. So you see the red values that you see are the targets and the blue values are the outputs of the untrained neural network. So it will now try to train it using by minimizing the mean square error. Now there's a command called a divide function where you could have divided it to a train set, validation set, and a test set like we discussed. So you could have told that put 70% in training set, 20% in validation set, and 10% in test set. Okay, I think the default is that, so I have given that don't because they're 94 points, so don't make any such change. And now I'm going to tell that, run up to 700 epochs. That is, if in 700 epochs you don't reach the mean square error of 0.001, which is my target mean square error, you anyway exit because it's not getting anywhere. Okay, so I will also then define these, and now I'm ready to train my neural network. Okay, and so I will issue. Oh, I deleted it. I had to press F9. I'm correct, no? Is it F9? Yeah. You see, it opens up. So if you type NN train tool, okay, in MATLAB, it will open up this and you can start, or NN tool, sorry. So if you type NN tool in MATLAB, it will open up a nice interface. So you don't need to do this coding if you don't like coding and just want to, do drag and drop. That is possible. That is also possible in the identification toolbox, which I could not show you that day. So, instead of writing all this ARX and RMAX, you just type ident, IDENT. It opens up one similar kind of a GUI where you can, tell where is my training data and so on and so forth. Okay, so let's move forward. So now it has trained it. Now look at this diagram. This diagram should be eminently sensible to you. You can see that there is the input layer, there is a hidden layer, and then there is an output layer. So you have 3 neurons in the hidden layer, and you can see this 3 written here. You have 1 neuron in the output layer, which, as you can see over here. The hidden layer, this diagram shows you a log sigmoid. It's that S-shaped. And this straight line shows you a linear function. So essentially the output is y is equal to W1 times the output of the first hidden neuron plus W2 times the output of the second neuron plus W3 times the output of the third neuron of the hidden layer. Because output layer is just pure linear. Whatever is coming in net, it just throws it out. Okay, or it just projects the same. Okay, now you can see over here, we have said Bayesian regularization, train BR, being that that particular training algorithm. So we could have used train LM also, but we chose to use train BR. Then you have mean squared error as your performance index. Okay. I'm not clear what is this. Maybe it is a max function of Matlab. Now see, I had told that you can go up to 700 epochs, but it stopped after 46 epochs. Okay, this is the time given to you over here. And the performance goal was given to us was 0.001. We had said that, good performance means your your squared error should be less than 0.001, and it has stopped at 0.004. So neither did it complete all the epochs, nor did it complete all the performance goal, but it stopped. It is telling you the gradient information, okay? And you can see one of the reasons why it stopped was this value of mu, okay? And the value of mu is the Markov sensitivity parameter, and that value has exceeded its maximum value of 1 into 10 to the power of 10. So, all these are methods by which a code can stop running. It's something with which there has to be an exit criteria. It may not converge, and it cannot just go on and on. So there are some exit criteria which are built in, and all of these are exit criteria. Performance goal is an exit criteria. Number of epochs is an exit criteria, and so on. Now, you should be able to see as to how many weights and biases are there in this neural network. Okay, so you had one input, 3 neurons, so 3 weights there, and then 3 weights from the hidden layer to the output layer, 6. And you have 1 neuron in the output layer, so 1 bias there, 7, and 3 biases in the 3 neuron hidden layer, so 10. Okay, you had 10 parameters. Now, when you use Bayesian regularization, it also gives you something called effective number of parameters. So if you were using a frequentist approach, it would use all 10 parameters. But a Bayesian regularization automatically tries to fit that effective number of parameters. Effective number of parameters means that although you have 10 weights or 10 parameters, it is not using all 10. Okay, it is just using 8.4 out of those 10. Okay, and this is the sum of squared of the parameters. You remember it was lambda times w square, and that value is projected to you over here. So it can plot, it does very nice plots. So you can see that the training is here after 20, after a certain number of epochs, it stopped. I mean, it is suggesting that stop your training here. I did not use a validation set. I could have used a validation set, and it could have done that early stopping, but in this case, I have not used it. And it will also show you regression. So it will show you the data versus the fit. Okay. So with that 45-degree line, how does the data in the fit look like? And it gives you the R value, okay, or the fit value. Now, of course, after I have got this, I could use on my end, simulate that neural network. Now, this is a trained neural network, and check on my plot, how did it work? So I'm going to do that over here, and let us see what the results look like. So you can see this is how the results look like. The black circles are the trained neural network output. So you can see that it did well in certain parts, but it didn't necessarily do well in the beginning part. It didn't get that first peak. Okay. So what will you do if you didn't get it? So one is, because this is a non-convex optimization, you could try to rerun this. And it might just happen that if you rerun this, it might just give you a better output. Okay. So since I have the written up, I will just issue the command, and let's see if it gives us a better output by hitting the run button. So this is the untrained neural network. Training is over, and now we should be able to see the And you can see that I have not made any change. The only difference is that the initial weights and biases are different. And you can see that the performance of the neural network has changed. So with different, because this is non-convex optimization, and the initial guess value plays a role as to how well that neural network is performing. Somebody might say that this is better. I might just run this once again. So it is a clear all, and then you can see the initial weights and biases lead to this. And if I hit enter, it shows very similar to the first one. It didn't do very well. Okay. Now, another opportunity that I have is to increase my number of parameters. Because I'm using a Bayesian regularization, I don't break it into train and validation set, but I can increase the number of neurons in the hidden layer to 4. Let me increase one more. And let's run this. So this is my initial neural network, now with 4 nodes in the hidden layer. You can see that the performance has definitely improved. But of course, with 4 neurons, you will have 12 parameters, okay, in this problem. And so you have increased your effective number of parameters, or maybe it's 13. And so instead of 8 effective parameters, it is now using 11.3 effective parameters. In the previous case, with 3 neurons, there were only 8 point some effective number of parameters. So effective number of parameters is a trade-off between how much importance to give to that initial weight that you have chosen versus just minimizing the mean square error. So it's some kind of a trade-off. And so that is a specialty of Bayesian approaches. Okay, so I hope that was clear. That example was clear. Uh, you know, okay. All right. Let me look at a classification example. So in a classification example, so there is no difference, right? I'm just going to solve the same problem, but only difference is that I'm using this exclusive OR. So 1, 1 and 0, 0 belong to one category. And so the targets are 0 and 0. And 1, 0, 0, 1 belong to another category. I'm going to use a multi-layer perceptron, though in the class we saw that you could solve it just by inspection using a radial basis function neural network. So again, I have given P, okay. So let me just just the same thing. I've just um, written on that. So this is the P. These are two. So new FF. So let's just get the syntax. P is the input, and then it looks like I put 2 nodes in the, or two layers. Oh, okay. Let's just make it 1 layer and see what happens. If needed, I will just increase it and make it 4. Now see, I'm going to put log sig here, and I'm going to put hard lim. Hard lim is that yes, no, because I know that the outputs are 0 or 1. Okay, and see how it performs. So it's probably going to be very similar. So I'm not going to run it one by one, but just see how, just run this code. So this is the exclusive OR example. You can see that there is an error. and I should let me just see what it. So this one, this zero, the red zero here, and the red zero at the other end are the two targets, and these two are the other two targets. And I believe it was trying to train it. So the circles, the black circles will be the made some change. Let me just go back and re Control Z. Okay, let me just try to run it without, maybe there's some change in the number of some dimensions, and just try to run this again. All right. So you can see that it has opened that same this thing. I have used now two nodes in. So so there is one node over here, one layer over here, and this is again the output layer. So it's again one single hidden layer. Okay, and you can see that there is a log sig and a log sig here. We didn't take a train LM. The number of iterations allowed were 1000. It stopped after 20. The performance index was 0, which is unrealistic, and it gave a very, very low value. Okay, and the mu value was here. So I think it probably has performed quite well. So let's see how well it has performed. And these are my so the red circles were the targets, and this blue cross are my trained network, and the black circles are the untrained, the initialized neural network. So you can see that initially the four outputs, one was over here, the first one, second was here, third was here, fourth was here. Whereas my targets are 0, 1, 1, 0. Okay. But after doing the training, it could correctly get all the four targets. So this is an example of, so, you can solve the same machine you can use for either classification, or you can use it for regression. Okay, so that was the point I wanted to make. So let me, as I said, let me go ahead and talk about some of these modern neural networks. And so I can start with a convolution neural net. Um, so are there any questions that, just to summarize? Otherwise, I'm going like a runaway train. Are there any questions that anybody would like to ask, or any comment or your experience that you would like to share? Okay. So it there's an initial barrier, but it's surprising that if you involve students, they can very quickly uh, get to working and solving problems and so on. And if you have not got one, so they call them boot camp. There's some website called boot camp, and rightly so, because you know most of the things and you also know your problem, but you have to go through that boot camp to start coding and all that. So, and there are a lot of I'm really surprised that there is huge amount of information on the web. In fact, you will see that almost everything that I have on these slides have been picked up from some website or other on the internet. So you can just start by going through some website, and you can start working directly. Okay, so let me do this deep learning using convolutional neural networks. So CNN networks, um, CNN networks are really. Let me see if I can bring. Okay, so CNN networks are really became very popular for image processing. Okay, and one big difference between image processing on the net and as technical data or plant data that you might be interested in is that there are millions and millions of images on the net. So whenever you are uploading something somewhere, that probably is a training set or a part of the training set for some neural network somewhere. Okay. Whereas that is not true about industrial data. If you're trying to use it for industrial data or for some experimental data, the data is quite limited. And so it is still to become clear whether these some of these neural networks will work successfully with process data or with industrial data. Okay, because they are deep neural nets, and they it requires a huge amount of data. Now, in case of image analysis, that image can be thought of as a uh, as an input P. Okay, so we said that the image is P, and it can be thought of as P. And if you're wondering how, then it is like this: that if you have an image and it is pixelated, okay, then all I need to know is the intensity of each pixel. So an image is, if it's a gray scale image, it is just a matrix. This is my input P. Okay. If it's a color image, then and the intensity is 0 for black and is 255 for white. So it's only a number, an integer between 0 and 255. So you can imagine that it's very straightforward, you know, to be able to store it. Now, if the color image, then as shown over here, and I've not now put. Oh, there is I've tried to make sure that I write the website name from where I've picked up these figures. Um, so in this case, you can see that it's a color image. So this is red, green, and you have the intensities for each of those. And so it essentially becomes a matrix, a 3D array. Okay. In this case, it is a 4 by 4 by 3. And where is that 3 coming from? It is coming from this RGB. So you can store any image. So it's a very, so if you download, let us say, your own image in Matlab, then you can open it up and you will see that it's just a 3D array of numbers between 0 to 255. So you can randomly filter that image and then save it and convert it back into an image and see, and you will be able to see, oh, the image has changed because you went and played around with it. So the input is very clear. Okay. So in this case, for example, you want to do handwriting recognition. So this is a handwritten digit. So one of the data sets which is there, I think it was CFAR data set, has some 60,000 handwritten images of digits from 0 to 9. So there's a label, right? There is the label C1 plus to C10, or if you would like, C0 to C9. Okay. And you would like to know, so essentially, as I said, what we are trying to do through ANN is just find the posterior probability that given this data matrix, 3D array, what is the probability that an image is it belongs to one of these 9 classes. So remember that these classes are essentially the digits. Okay. Now, in case of you could say, see, I've already learned feed-forward neural network. Okay, and I can just convert this 3D array into, I can vectorize it. So I can just make it into one long vector. Okay, and then put one feed-forward neural network, backpropagation neural network, and get that classification done. So I there are different ways of coding. So one is one way of coding for, so if it is 0 to 9, so I can code it like this. I can do 1 0 0. This is digit 1. Then I can put 0 1 0. These are my targets. Okay, so this is class 1, this is class 2. So like that I can have 10 classes. This is known as one hot encoding. Okay, so it is known as encoding those targets. And in this way, you can get your targets in place. So you have now X or P, and these are your T's. So if your P is now a 2D or a 3D array, I can just put it in one very long vector. Okay, and go ahead. But you will see that, see, if I have a high density image with 8,000 with 8K resolution, okay, which is not unusual. Okay, even our mobile phones have better resolutions than these. Then you see your vector would become this big, millions. 7 for the 28, so it will be more than 28 million size of the vector. And so image processing using backpropagation neural networks is difficult. And it is difficult. Either you take some very, very low resolution image like this, you can go back to that Matlab code and you make it into a vector, give the classes and let it train. Okay. But because images can have a lot of information in it, or are large data sets, each example itself is large. This is where CNNs come in. So what CNNs do is they say so this is the brute force approach, that you just vectorize it and put one feed-forward neural network or a backpropagation neural network. So what CNNs do is they introduce some more layers, and one is known as the convolution layer, and then this is then a pooling layer, and finally they have the backpropagation neural network, or the MLP, which we have already seen. Okay, so they have figured out something, that when you look at an image, you need not carry that full million element image with you, which has millions of elements. It turns out that there's strong degree of correlation in an image. If here there is a pixel which is of a certain intensity, then the next pixel is also of a similar intensity. Okay, of course you will say, if there's a sharp edge in my image and then suddenly the intensity changes. So you say, yes, I need to be able to pick up sharp edges. I need to be able to note that if they are similar, then I don't need to keep all those pixels. Okay, there is a lot of correlation within those pixels. So this convolution layer does that feature extraction for us. Okay, and this does downsampling. So it says, okay, I'm going to reduce the numbers because I don't need all of that. And then this downsampled vector is then what they call as flattening. Flattening is converting a matrix or a 3D array to a 1D array. Okay, and this then goes into your multi-layer perceptron, this to your number, and you can have many convolution layers, you can have many downsampling layers, and this also tends to be quite large, the MLP, or the multi-layer perceptron. Okay, this is what a convolution neural net is. So it can have, 30, 40 layers, and they work. So it has been shown over here. You have an input image. First, you have a convolution step, and then you have this downsampling step. So if you know, and these steps are unbelievably easy to do. So there is, in a convolution layer, there is a weight, and so again, it's the same idea that you have an objective function of a net, and this net is nothing but W previous layer inputs plus bias. So these basics don't change. Okay. So I saw that there was a very nice video on convolution neural networks on MIT's website, which I picked up just to show that, see, there are certain features of X. So one big problem with an image, which is quite peculiar to images is, let's see, if I have a face, okay, and I read it, and then if, let us say, this face is rotated, let me make it a long face. If the picture is rotated, it should be able to say this is the same person. It should not say that this is a different person and this is a different person. They both should belong to the same class. Okay. So what you can do is that, although or the person is slightly different in one image versus the other, so there are certain features. For example, over here, you can see that this feature is over here, okay, and it seems to be in the same place of that image. But you can see, like, this feature over here, which is just starting from here, is at a different spot. It is starting over here. But these are equal. They're the same feature. So if the image is rotated or distorted, I should still be able to look into these peculiar features and not be bothered about what is their location with respect to the frame, if I may say that. Okay. And so if these features are similar, then I should be able to understand that these belong to the same class. So if I may go forward, so as I said, that a very popular activation function is the ReLU or activation function, and which is given by this. So it's not that logistic sigmoidal that I spoke to you about, but it's just a ReLU function. It's still zero. It is zero, and anything after zero is just, on the negative side, the output is simply a zero. On the positive side, the output is simply the input. And I think, this is because you have numbers between 0 to 255. So negative intensities may not make sense. And so have to keep it like that. So how do you calculate the output of this? You have, so in this operation of convolution, this is, let us say, this is a matrix. You take a patch in that matrix. Okay. And these are the weights, 1, 0, 1. So you do a product, element by element product between W and that patch. That patch is over here. Okay. So I'll just call it as patch plus the bias term B. And that you ReLU it. This is the output of that neuron or the convolutional neuron. Okay. So for example, if you do this here, if the weights were 1, 0, 1, 0, 1, 0, 1, 0, 1, and you multiply it with the intensity level, you get an output of 4. That is the convolved feature. Okay. So you go patch by patch. So first you did this. Next depending if your stride is 1, then you just go one cell to the right. Then you go one cell to the right, and so this you fill here, and then you fill this one over here again, and so on, and then come down. So this is going to be your next stride. Okay, so this is known as stride length. You can also choose to go 2, or you can choose to go more. Okay, This operation is known as convolution. Okay, so I'll skip some details, some very nice graphics which people have made and posted on the web, which helps us understand. Go to downsampling. So the weights are unknowns which are going to be determined by the ANN training during the training phase. Okay. So, some examples of weights I got from Wikipedia, and I saw that, see, if you didn't want to train and so on and so forth, so if you take some image, okay, and you multiply it with this weight vector, so this is already preordained weight vector, you get the original image back. If on the other hand, you are trying to use a different weight vector, like shown to us over here, this image of this animal changes to this. So you can see that that image has changed. Okay. So these, what you have to remember is that these different weight vectors end up filtering that image in a very different way. But we do not use these different weight vectors. What we in fact do is just identify these values. So these all are unknowns for us. Okay, W and B, just like in the previous. This is only to understand that there are certain weights. When you do that convolution operation, it can do an edge detection, it can sharpen it, or it can give you an identity, which means the same input again. Okay. To blur the image, they suggest using this. Okay. So I'm assuming, in a lot of these Photoshop or image processing kind of apps that we have on our mobile, I'm not sure, but I'm just assuming that it must be just multiplying. If you want to make it sharp, then there's a particular weight that it must be using. If you want to blur it, there's another weight that it is using, and so on. Okay, so what happens after convolution layer is that you've done some kind of a feature extraction. Okay, but that is too big to flatten it and make it into a huge vector. The cost for training that MLP is going to be too large. And so what we do is actually try to reduce the size of that convolved matrix. And a simple way is you take this over here, and let's say you do max pooling. So if you do max pooling, the largest number is 6, you just put it here. The largest number is 8, you bring it here. Okay, and there is no straddling like it happened during convolution. So these do not overlap. Okay, so this is one way of doing pooling, or you can do an average, or you can take a sum. But essentially, at the end of this exercise, you are able to downsample it. So now that image is becomes smaller in size. Okay, so you can have many downsample layers. So it can become significantly smaller. And finally, after you have done the convolution step, okay, and you have done, so you can see this is the convolution step, this is the pooling step, convolution, pooling. Now is finally that multi-layer perceptron or the feed-forward neural network. So this is the flattening step over here. Again, this slide is taken from that MIT website. So this is flattening, where you take this downsampled matrix, you flatten it, okay, and then you have this multi-layer perceptron, which could have many layers. Okay, for example, you could have a softmax function here, and it could do an identification. So this example on their in that video, they've shown a car, and given an image, you have to be able to classify this. And so for example, in driverless vehicles, you want to be able to, it's not just the image, it's not just that information, but from that information you want to conclude that this is a human being that is crossing the road, I need to slow down. Okay, or that the light is red, or there's a vehicle ahead of me. So we need to be able to not only capture that information through cameras or other means, but also to be able to give some kind of a meaning to it, which happens through convolution. So this is the final step. So you did convolution, then you did downsampling, and now is the mixed, sorry, not mixed layer, but multi-layer perceptron. And that, as you all know, we've already seen, this is an example of a multi-layer perceptron, and this will be 4, 4, 5, 6, 3, 3, 3 neural network. Okay. And softmax function is very popular for classification, multi-category classification. So again, let me conclude this part by saying that, convolution neural networks have become very popular. As I told you in the beginning or in the last class, that this AlphaGo is this Go game, and AlphaGo was was the convolutional neural net that could consistently beat the human champions, and that, I think this happened. It was published in 2017, somewhere in 2016, and after that it became extremely popular. Okay. Some of the popular CNNs that we keep hearing in the media is GoogleNet, LXNet, and there are some more. Now these, some of these neural nets are freely available. Okay, and the idea is that they are partly trained. So if it's an image processing deep neural net, then they know that some, in the some layers capture the broad features, some layers capture the specifics. So you don't have to start from ground zero. You can take a previously trained neural net, and using that previously trained neural net, you can go ahead with your application. Okay, so I spoke to you briefly about deep or convolution neural nets. Let me talk another very popular neural network called the recurrent neural net. So the recurrent neural net is, was, so 1986 when you had the backpropagation algorithm. Okay. And I think, right then and there, people came up with why not have a recurrent neural net. And very early, we had algorithms, which was, so while this is a backpropagation algorithm, BP, this was known as backpropagation through time. Okay. So the recurrent neural net, as you can see, the output is, so this is an input, and h of t is your output in this particular case. So this is like your y, and this is your dynamics, okay, like shown over here. So this is like a proper difference equation. So the way that you could easily train such neural nets using the backpropagation algorithm is by recognizing that these neural nets can be unfolded in time. So see, this is time. So I could put a delay over here. The Q inverse operator. Okay. So I know this is yt. Then what goes back over here, because there's the Q inverse operator, is yt minus 1. Okay. And so there's a delay operator, and I can keep feeding the previous outputs to the RNN. And this can be opened in time. So this is my input at 0. Okay. And then I have that the output is now given to the next ANN at time 1. So you have unfolded. So if you break this, okay, and you replicate this, you will end up getting this. You've unfolded it in time. Okay. And so basically you made it into a feed-forward neural network. But there is a big difference. And the big difference is, when I looked at feed-forward neural networks, each layer had its own weights and biases. So this had a different set of weights and biases. I would call it W1, I would call this W2, and so on. But here, you can have this different. You can't have W1 different from W2 and so on. Okay, because it is what we would call as linear time invariant model. You can't have that, if you have some fixed law, not a good idea. Okay, some alpha times, not a good idea. Okay, not fixed law. I was thinking of Fourier's law of heat conduction, but I didn't want to go to partial differential equations. But the Fourier's first law of heat conduction, if you think in on those lines, you will realize that these parameters which are equivalently being captured by the weights and the biases cannot keep changing over time, right? Unless it's a time varying system. So if I have a heat exchanger, then my fouling could make it a time varying system. Okay, but we don't model it like that, right? We just model it as some heat transfer coefficient. So the same thing is true over here, that this W1 and W2 cannot change. Okay, and so that is a big difference between a regular backpropagation algorithm and this unfolded in time, which is really a dynamic system which you have unfolded in time. So again, you unfolded RNN is simply a MLP, multi-layer perceptron, where each forward layer corresponds to passage of time. I've already said this, that you cannot have it as time varying. Now there was a problem when you don't allow it to be time varying, and I'll just tell you what that problem is. Okay. So we had talked about sensitivities, and these equations will not make any sense in this class. But we had talked about certain sensitivities and how you backpropagate it. So it turns out that because you have the same values of the weight, you end up requiring your activation function, okay, keeps getting repeated. So you have f dot, the derivative, and it keeps getting repeated. So it is some f dot multiplied by f dot multiplied by f dot and so on. And using this backpropagation through time was not giving very good results. Though theoretically there didn't seem to be an issue, it did not give very good results. So later in 1997, these two researchers, Hochreiter and Schmidhuber, showed that it turns out that because you keep on multiplying, then either this derivative vanishes. If let's say the value of this derivative is less than 1, then you continue multiplying. Let's say it's 0.8, so it becomes 0.64 multiplied by 0.8, it keeps on, it vanishes, okay, or it explodes. And the impact of vanishing means that the memory over here is not carried after many time points. Okay, it vanishes. This memory is no longer being carried forward because of that vanishing gradient. So the authors then suggested a different neural network called the Lstm neural network. Okay, so they showed that the recurrent neural nets do not have long-term memory. They seem to have short-term memory, particularly when that gradient vanishes. So again, I've most of this from the net. So for example, if you're doing text processing, natural language processing, and you say clouds floating in the, so you know that this is sky. Okay, this is short-term memory. It will remember that if you get a word like clouds floating, it'll, and so you can use RNNs or for writing a story, for example. Okay, because they have studied some kind of correlational information and they can try to build it up. You give it some input and it'll keep adding words and make a sentence for you. But if you have a big sentence, like again, I picked this up from the web, like I grew up in France and there's a lot of other stuff. And then finally you say that I speak fluent some language. Then for me as a human being, I would understand immediately that, okay, this person was talking, or the context was France, and so it will put here French. Okay. But for a recurrent neural net, it's not easy. It's not an easy thing to do. So they came up with some new methods with a changed neuron. So they came up with as an LSTM neuron. Okay, so we don't use the standard neuron that we discussed in MLP, but we use a different neuron, which was again given by the same authors, known as the LSTM neuron. And without getting too much into the detail, um, what this neuron had was it carried forward some state information, okay, which is given by C, and from one neuron to the next, it went to the next level, and it had these gates, which was a critical element of these LSTM neurons. The gates had the ability to decide that how much information of that cell state we want to forget. That means when we go from one neuron to the next, how much of this information we want to forget. Okay. If you get a new piece of information, some new input u or x, the independent variable, how much of that to take it forward. Okay. And it also had the ability to, so it became like a state and an output. So H was the output and C was the state. Okay, the state is only being conveyed from one LSTM neuron to the other, and the output is what you get is the output of the neural network at any given time. And it was not very difficult. Each of these four operations had simple operations like in the original neuron that we had seen, but if we put it together, this is what an LSTM neuron looks like. Okay, and this apparently removed that problem of vanishing gradients, that it could decide from the context. That means it got a long short-term memory. So it's a long short-term memory. So the short-term memory of a recurrent neural network could be over a longer duration. And these recurrent neural nets are, for example, used, for example, if I have a first principles model, I can use it for predicting it using an LSTM. I could also use it for speech processing, for translation. Um, we all have heard about this Google Voice, and also for making musical composition. So the CNNs can make artificial faces or synthetic faces. These are not real people, but it takes images of people and makes its own synthetic faces. And uh, so this is what I thought I would talk to you in terms of uh, neural networks. Now let me just talk to you very very briefly about TensorFlow. Uh, as I said, that this TensorFlow by Google, okay, and as soon as I said Google, my mobile phone said, "How can I help you?" Okay, so yeah, so it was built by Google, and it's like a very, it can do very sophisticated operations, and it has become like a standard which is used by everybody. It's open source. So as I told you, you can use it in R, or you can use it in library in Python, and the same software. So um, um, so you have it also allows you to do parallel processing. So for we keep hearing about ANNs using parallel processing. So it doesn't use a CPU, but it uses GPU. So Professor Nataraj of Systems and Controls does a lot of work on GPU, where there is a different software or programming language called CUDA, which is used. And um, for example, you know, I was speaking to somebody who is making a nutritional app, and they said that for a user to be able to tell what was the nutritional content of their food, they have to just take a photograph of their plate and you upload it, okay, and the different food groups in the image being consumed will go into finding out how many calories you have eaten and so on and so forth. So there are these really lateral applications which is left to our imagination, and you can come up with any application. For example, I had seen an industrial application where in some mineral processing, shale gas processing, there was you could not make out this interface because it would get dirty between one phase and the other phase. And so it would get dirty, but if you image it and you pass it through a CNN, then it could more accurately predict where is that interface. Okay. So, as I said, I did not have access to my R, and I realized I could not install it. But this is extremely simple to do. Um, and because many times these codes are available on these websites. You don't have to write from scratch. And I have, for example, used it with some of my students, or in teaching a course. And you had data sets. You could, this was images that you could get from the data set. And for the most part, you only have to make some changes. But you can start using, you can plot these different images. You can decide how many convolution layers, how many max pooling layers you want. You can define a neural network in this TensorFlow. So Keras is a very high level interface so that you don't have to do everything, because there's so many things to do. So you need not try to, it's a very high level interface which can get you started right away. So you can define how many pooling layers, how many convolution layers, okay, and so on. And it's fairly simple to use. And then at the end of it, you can add this to your model. You can flatten it, and you can say, okay, I want uh, 64 units from my first hidden layer, and the output layer there should be 10. And it's fairly straightforward. So I think it is 3:20. So let me stop here. I can take any questions that you may have. So I went through quite some detail in the hands-on session, but I thought I would talk about the CNN and RNN and the LSTM because these are very, very contemporary networks which are being used by by researchers, or keep reading about them. And also the software TensorFlow is extremely straightforward to start using. So I will stop talking. I will see if there's any question from the participants.
Hello, sir. I have a question.
Yeah.
Sir,
Yeah.
you said in recurrent neural network the weights remain constant.
Yes.
So that is also true in normal MLP, right? Once you train it, the W remains constant, right? Or you mean as the
So
epoch progresses,
yeah.
the
So
W?
yeah. Let me try to show that with help of a. So see, let's say there is an MLP. Okay. So in the MLP, you have one layer, you have another layer. So this could.
Are you sharing something? I'm not able to see.
Oh, yes. Thanks. Let me say share. Are you able to see this one note?
Yes, sir.
Okay. So, so I'm trying to draw an MLP. So see, this is one weight. Okay. These are another set of weights. You're going from layer to layer. Now think about an RNN. And RNN should originally have been like this. That there is two inputs and you are putting it back and there are other inputs. So if I want to use the jargon of time series, I would say this is U of t. This is Y of t. Okay. Now, if I want to represent this as a feed-forward neural network, what would I do? I would say that, okay, this is my U of t. I will need one initial condition, Y0, and then I will get Y1. Okay. Now, I'm not feeding back like over here, but I'm going to show it as a new layer. And here will be my U1. So this was U0. Now is my next time point. I will put it as another layer. So this is my Y of 2 and U of 2. Now you compare this RNN with the MLP. See Y0, let us say my model is Y of t is equal to 0.5 times Y of t minus 1 plus U of t minus 1. Okay. So whether t is 1 or t is 2, this parameter is the same. You cannot have this parameter that here there was one set of weight and here there was another set of weights. So these weights have to be identical when you open it in time. Otherwise, it will become that y of 1 was 0.5 times y of 0, but y of 2, if let's say here was 0.5 and let's say here is 1.5, then y of 2 is equal to 1.5 times y of 1. So you have the same weight has to appear here. It is what we would call as a linear time invariant system. Otherwise, you are saying that my parameters are time varying. So that is why here the weight should be same if I open it up. Whereas here, this in the original just had one set of weights here, another set of weights here, and you can adapt those weights to give you a good, performance.
Okay, sir. Yeah, understood. Thank you, sir.
Yes. Any other question? So I think at 3:30 is supposed to be the concluding session, and I would like I think Professor Goody will join that session. So maybe we can just take like not log out and just take a 2-minute break and join back at 3:30. I will leave the video on. I'll leave the session on. Okay.
Okay, sir.
Yeah. So let me stop recording.